In this video, we're going to talk about a different type of limit than we've been talking about before, and that is the limit at infinity and the limit at negative infinity. So first, let me give you the definition of the limit at infinity. So we need a function defined on some interval from a off to infinity on the x-axis, so its domain includes that. Then what we'll say as the limit is the limit as x goes to infinity of f of x is L if the values of f of x can be made close to the number L, closer and closer to the number L as we like, by taking values of x that get larger and larger. So instead of the x values going to a specific number, we're just going to take larger and larger x values and take a look at the corresponding y values and see if we can see a pattern there. And if we can, if those y values get closer and closer to some fixed number, then we'll say that number is the limit. Likewise, we take the limit as x goes to negative infinity of f of x. In this kind of limit, we're looking at values of x that get smaller and smaller. Right, again, by smaller and smaller, I mean bigger in absolute value, but with a negative sign out in front. So really far to the left on the number line. So as x values get smaller and smaller, the corresponding y values, the values of f of x, will get closer and closer to the number L here. Okay, so let's take a look at just some numerical examples to just kind of get the idea of what these limits mean, and then we'll also take a look at some of the graphs. All right, so our first example here is the function x minus 2 over 3x plus 1. Over here we have a table of values and that we're going to look at to make some conclusion about the limit as x goes to negative infinity. All right, so here we have some x values that are getting smaller and smaller, right? And over here on the right side of the table, you see their corresponding function values, the y values here, right? And it looks like as the values of x get smaller and smaller as they go to negative infinity, right, the y values are going to positive 1/3. So the closer the y values get to 1/3 here, or 0.3 repeating. So we would say the limit as x goes to negative infinity of this function is positive 1/3. Over on this side, on the right side, we have x values getting larger and larger, right? So the x values are going to infinity. And here in the right column are the corresponding y values for those x values. And we see a similar behavior to what we had there before, right? Those y values are getting closer and closer to 1/3. So the limit as x goes to infinity of this function is going to also be positive 1/3. Here's a graph of that same function, and here I've marked 1/3 on the y-axis, the line y equals 1/3 as a dotted line right here. And so graphically what's going on is as the values of x are getting farther and farther this way, the y values are getting closer and closer to 1/3 to that where that dotted line is located. Same thing here as I go off to negative infinity. And as you can see there, this graph does have a horizontal asymptote at 1/3. The graph gets closer and closer to that line the farther you go off to the right or to the left. All right, here's another function, sine of 3x over x plus 1. Okay, and here we're taking the limit as x goes to negative infinity numerically, so we would just look at some x values that get smaller and smaller, take those and plug them into the function and find their corresponding y values. And while they do oscillate around, you can kind of see that they get closer and closer to 1. Sometimes they're bigger than 1 like this one, and sometimes they're a little bit less than 1. But every time you can kind of see another digit here. I have 4 9s, right? And then here I have 5 zeros, and that pattern kind of continues here. So even though the values get bigger than 1, smaller than 1, they are getting closer and closer to 1, just on different sides of 1. When we look at the limit as x goes to infinity of sine of 3x over x plus 1, so here we're taking x values that get bigger and bigger. Here we're looking at their corresponding y values. and we see the same sort of behavior over on this side. We see that these y values, even though some are less than 1, some are bigger than 1, each time they get a digit closer and closer to 1. Okay, so on both of these, the limit as x goes to negative infinity of sine 3x over x plus 1 would equal 1. And over here, also, the limit as x goes to infinity of sine 3x over x plus 1 would also equal 1. Here is a graph of sine of 3x over x plus 1. And you can see the farther that you would go off to the right here, the graph does oscillate back and forth like the regular sine function does. But you can see those oscillations get smaller and smaller. So the y values are going to get closer and closer to 1. And here, same thing, as I go really far off to the left, the y values again get closer and closer to 1. All right, our next example that we want to look at is the tan inverse function, the inverse tangent. So over here again we have the limit as x goes to negative infinity. We're looking at a bunch of x values that get smaller and smaller, and here we are looking at their corresponding y values, and you can see a definite pattern here. These values are getting closer and closer to this decimal here, minus 1.57079. And that happens to be negative pi over 2 is what that number is. The limit as x goes to infinity of inverse tangent, here we're taking x values that get bigger and bigger, and then we plug them into the inverse tangent function, and then we can see that the values of the output values, or the y values, get closer and closer to positive 1.57079, which will be positive 1, or just pi over 2, right? The positive version of this, the opposite of that one. Okay. All right, and let's take a look at the graph of inverse tangent. And here you can see the graph of inverse tangent with its two horizontal asymptotes, one here at pi over 2, right, around 1.57, and that's the limit as x goes to infinity of inverse tangent would be pi over 2. And then going off to negative infinity, the limit would be negative pi over 2, around negative 1.57, around in there. So you can see this one has two horizontal asymptotes here. All right, in our final example, we have cosine of x, and we all know what cosine x does, right? It sort of oscillates back and forth between 1 and negative 1. So if we take the limit here as x goes to negative infinity, we look at smaller and smaller x values here. We can see there's no real consistent pattern here with this at all. These numbers just sort of bounce around, so you can't really find any pattern here. So in this case, the limit as x goes to negative infinity of the cosine function, it just does not exist. And a similar behavior over here, if we look at the limit as x goes to infinity of cosine x, we'll take a bunch of values of x that get bigger and bigger, and take a look at the corresponding y values to see if we can see any pattern, and it's the same as what we saw over there on the left side. In fact, exactly the same values. Can't really find any noticeable pattern here, right? And for good reason, right? We know that the cosine function just oscillates back and forth. So again, this one, the limit as x goes to infinity of cosine x, it's just not going to exist. So it does not exist on both of these. And when you take a look at the graph, right, we all know what this graph looks like, and we can see there's no horizontal asymptote here. It's just bouncing back and forth from minus 1 to 1 constantly. So there's no horizontal asymptote. The y values don't get closer and closer to any fixed number. So the best you can say in this situation is just that these limits do not exist. All right, so we've taken a look at the limits at infinity, so the limit as x goes to infinity and the limit as x goes to negative infinity from the numerical point of view, right, and also from the graphical point of view. So we're going to talk a little bit more about when you have infinite limits, when you take a limit at infinity, and then what we'll do is talk about the analytic approach. How would you find these limits without looking at numerical data or looking at the graph? And we're going to see that it's quite a bit different than what we would do if we were taking the limit at a specific number, like the limit as x goes to 5. That approach is not going to work for the limits as x goes to infinity or the limits as x goes to negative infinity. But we'll talk later on about exactly how we will do those limits.